Hey everyone, and welcome. Today, we're going to pull back the curtain on this whole AI revolution. We're going to talk about its silent, elegant, and just unbelievably powerful architect. You know, when we think about what makes AI tick, our minds usually jump to a couple of things, right? Just these unimaginably huge data sets and raw, brute force computing power. But what if I told you that's only a fraction of the story?
You see, while all that data and all those computer chips are kind of like the fuel and the engine, the actual design, the very blueprint that allows an AI to learn, to see, and to create, it's all built on something much, much more fundamental. The real secret ingredient? Well, it's math.
And to be specific, it's linear algebra. I mean, this is literally the scaffolding that every single neural network is built on. It's the language that translates our messy, chaotic world into a structured format that a machine can actually understand and work with.
So to really wrap our heads around how this all works, we've got to look at the basic building blocks. We're going to dive into AI's hidden foundation.
Okay, first thing you have to grasp is this. To a computer, everything, and I mean everything, is just numbers. A picture, a sentence, a song, it doesn't matter. A computer just sees a massive pile of data points. And linear algebra is the tool that gives all those numbers some structure, some meaning.
And the most basic piece of that puzzle is called a vector. The easiest way to think of a vector is like a digital fingerprint for any piece of data. It's really just a list of numbers, and each number stands for a specific feature. This is how a computer takes something from the real world and turns it into a single point in a huge mathematical space.
So, what happens when you take a whole bunch of those vectors and stack them together? Well, you get a matrix. And folks, this is where the magic really starts to happen. A matrix is just a super organized grid of numbers, but its structure is what allows a computer to process just enormous amounts of information all at the same time.
And this right here is the whole ballgame. Instead of looking at one number, then the next, the system can do one single operation on the entire grid at once. This parallel processing idea, well, that's exactly what modern GPUs, the graphics cards and gaming PCs, are built for. They are absolute masters of matrix math, which is exactly why they've become the backbone of the entire AI industry.
All right, so we've got the building blocks down. Now let's see how they actually let an AI make sense of, well, reality. So let's say you show an AI a picture of a cat. It doesn't see cat. It doesn't see fur or whiskers. Nope. It sees this, a giant matrix. And every number in that grid corresponds to the color value of a single pixel. The entire cute cat picture is just a grid of data waiting to be interpreted.
So how does it get from that giant grid of numbers to actually identifying the cat? It's all about a process of transformations. The AI takes the image matrix and multiplies it by other matrices, and these act like filters. So one filter might be really good at highlighting vertical edges, another one might be great at finding textures, and layer by layer it combines all these patterns until it can finally say with a high degree of confidence, yep, that's a cat. It's all just matrix multiplication, over and over again.
Now, what's really fascinating is that this exact same logic applies to something as complex and nuanced as human language. In the world of AI, words can be treated like mathematical objects too. They have relationships that you can actually measure. For instance, the relationship between king and man is, mathematically speaking, almost identical to the one between queen and woman.
Okay, so if we treat these words like points in space and do a little bit of vector arithmetic, what do you think we get? Let's say you take the vector for king, you subtract the vector for man, and then you add the vector for woman. What idea, what concept should you land on?
And there it is, queen. Now, this isn't just a cool party trick. This is a really profound demonstration of how an AI uses linear algebra to actually understand the meaning, the context, the relationships that are baked right into our language.
This is the absolute core of how large language models work. Every single word is turned into a high-dimensional vector, something we call a word embedding. Then the AI performs that vector arithmetic we just saw to figure out the meaning. And that famous attention mechanism you hear so much about? Well, at its heart, it's really just a series of very sophisticated matrix operations that figure out which words in a sentence are the most important ones to pay attention to.
And look, this isn't just for some far-off futuristic AI. Linear algebra is already the engine running so much of the technology that we use every single day.
Its impact is, well, it's everywhere. The movies that get suggested to you, the systems that are working to keep your data safe, the financial models analyzing market trends, all of it is powered by these exact same mathematical principles.
I mean, take recommendation engines. They use a technique called matrix factorization. They build this absolutely giant matrix with users on one side and items, like movies or products, on the other. By breaking down and analyzing this matrix, they find these hidden patterns in your taste to predict what you're going to want to watch or buy next.
Or think about something like cybersecurity. There's a technique called principal component analysis, and it helps systems sift through just mountains of network data to find the most important patterns. And that makes it way, way easier to spot an anomaly, that one little outlier that could signal a hacker trying to get in.
So when we bring this all together, we can finally start to look beyond this idea of AI as just some kind of mysterious black box. Because once you understand the role of linear algebra, that's exactly what happens. AI is no longer magic. It's a system of logical, predictable, mathematical transformations. The mystery kind of melts away, and it's replaced by this real appreciation for the pure elegance of the math that's running the whole show.
For anyone who's actually building this technology, mastering these concepts is it's non-negotiable. It's like a carpenter needing to understand the grain of the wood, or an architect needing to understand the physics of load-bearing walls. It's that foundational knowledge that lets you not just use the tool, but to truly innovate and build something brand new with it.
And that really brings us to the most important point of all. What we see as the most advanced artificial intelligence of our time is, at its very core, built on top of some of the most fundamental and beautiful truths of mathematics. And that leaves us with a final thought to chew on. If the entire architecture of AI is grounded in simple, elegant math, maybe the key to building a better future isn't just about inventing what's new, but also about rediscovering the fundamental truths that we already know. Thanks for joining us.